Strength of material. Strength is property. Material means here engineering material. Load causes deformation. Deformation resistance force. Resistance force causes stress. Stress is nothing but resistance force by area. Strength is material property. Strain is equal to delta L by L. Sigma epsilon stress or strain for mild steel diagram will be like this. This is lower yield point, this is upper yield point, this is ultimate tensile strength, this is failure point, fracture point. Sigma y f sigma a is equal acceleration is equal to f by m. If it is applied in this direction, will not move. Stress is equal to resisting force by area. Resisting force will be developed. Stress corresponding to lower yield point defines the strength of material. Design strength. Lower yield point defines strength of material. Because lower yield point is at almost same level as elastic limit within elastic limit. Safe working stress is equal to sigma y by FOS, factor of safety. Shear strength tau y is equal to sigma y by 2. Stress versus strength. Stress variable depends on applied load F by A. Strength material property does not depend on force. Stress internal resisting force by area. Pressure is intermolecular due to intermolecular collision in fluids. Fluid can apply pressure on solid or fluid, but solid cannot apply pressure on any other solid. Stress can be tensile, compressive, shear. Sigma is equal to F by A. F is input here. Always pressure is always normal and can be and compressive in nature. P is equal to F by A. Here P pressure is input, F for pressure force is output. F is equal to PA. In LPG cylinder, pressure will induce stress. Here pressure is input, stress is output. Types of stresses, this is normal stress. If it is applied along the cross section, then it is shear stress. Tau is equal to F by A. Can shear force produce normal stress? Yes. The force is applied like this, then here on top is a sigma tensile, here on bottom sigma compressive will be generated. Epsilon t is equal to delta x by x, pi is equal to x by y. Here pi is almost small, so this distance by this distance. Tau is equal to F by A. Modulus E is equal to Young's modulus of elasticity is equal to sigma by epsilon. G modulus of rigidity is equal to tau by pi. K is equal to bulk modulus is equal to minus delta P by delta V by V is equal to delta P by delta rho by rho. Compressibility is equal to 1 by K. Incompressible delta P is equal to 0. K is equal to infinity. Compressibility is equal to 0. What do you know about elasticity, plasticity, Hooke's law, proportionality limit? Elasticity, it is the property of material by virtue of which if we apply load on the body it will be deformed, and when we remove the load it will go back to original position. It is like spring. We can explain it by spring. If we apply force then it will go back. Plasticity, permanent deformation, failure failure of material yielding. Hooke's law, sigma directly proportional to epsilon, sigma is equal to A epsilon. Proportionality limit till where this is valid, sigma is equal to A epsilon. Factor of safety is equal to sigma y by permissible stress. Safe design, permissible stress is equal to sigma y by FOS. FOS, factor of safety of cycle is more than aeroplane of a cycle. By cycle means some bicycle is more than aeroplane because weight should be less. More factor of safety means more lifetime. More factor of safety means using more material. Poisson's ratio can be negative. Mu is equal to minus lateral strain by longitudinal strain. Property of material, which value minus 1 less than mu less than 0.5, my negative for some biological materials. 0 actually in practical 0 less than mu less than 0.5. 0.5 is for rubber, 0 is for cork. Engineering materials generally 0 to 0.5 only. Steel mu is equal to 0.3. Relation E is equal to 9 kg by 3k plus g. E is equal to 2g into 1 plus mu is equal to 3k into 1 minus 2 mu. Radial and volumetric strain sphere V is equal to 4 by 3 pi r cube is equal to pi d cube by 6. Delta V by V is equal to 3 delta r by r is equal to 3 delta d by d. Isotropic properties are same in all directions. Homogeneous, same chemical composition. If strain is zero, can there be stress? Yes, thermal stress applied when both ends are closed, strain will be zero. If external load is applied when strain is equal to zero, then stress delta L is equal to L alpha delta T, epsilon is equal to delta L by L is equal to alpha delta T, sigma is equal to E alpha delta T. Composite section to carry more load. Composite section. If it is loaded like this, P is equal to P1 plus P2, delta L1 is equal to delta L2, sigma by epsilon is equal to E, sigma delta L1 by L2, so sigma 1 by epsilon 1 is equal to sigma 2 by epsilon 2. P is equal to sigma 1 A1 here. If it is loaded like this, P is equal to sigma 1 A1 plus sigma 2 A2, and sigma 1 by epsilon 1 is equal to sigma 2 by E2. Sigma 1 by E1 is equal to sigma 2 by E2. Here E1 and E2. Brass, steel, alpha brass greater than alpha steel, quotient of thermal expansion. So brass will try to expand more, but steel will not let it, so it will be in between them. Brass compressive stress induced, steel tensile stress induced. uh, Due to self weight at a distance x dx a l sigma varies proportionally with x. Elongation due to self weight is equal to question mark. W is equal to weight by volume is equal to W by LA is equal to rho g. Sigma x is equal to W A x by A is equal to W x. D delta x by dx is equal to W x by A is equal to sigma by A. Delta L is equal to W L square by 2E. Complementary shear. What is complementary shear stress means? If you apply only tau in this direction, this will be reaction tau in this direction, but these two will be opposite side will also be generated. These are complementary to balance torque to be in equilibrium. These will be generated, so these are called complementary. If F is applied in like this, consider a cross section theta, then rotate f along this ftfn. Sigma n is equal to fn by ac. Fn is a cos theta, fn is f cos theta. Sigma t is equal to ft by ac. This is f sin theta. AC is equal to ab by cos theta. Sigma n is equal to sigma x cos square theta. Sigma t is equal to sigma x into cos theta into sin theta. Sigma x, sigma I, sigma theta. Principal stresses and principal strain in a principal plane at which sigma normal is maximum or minimum and tau is equal to 0. Two principal planes at 90 degrees to each other. Normal stress sigma, sigma less than or equal to yield strength. Shear stress tau less than or equal to shear strength. UTM and universal testing machine. W by A L, sigma max is equal to sigma x, tau max is equal to sigma x by 2. Universal testing machine, mild steel, W by A. Normal yield strength is equal to 2 into shear strength. Brittle concrete, brass, cast iron, ductile steel. Brittle, good shear strength, poor tensile strength, good compressive strength. Ductile material, steel, good tensile strength, poor shear strength. Sigma x, sigma y, tau x y. Okay, more this is more circle, sigma where it touches this axis sigma 1 sigma 2. This line is AB plane, A and B points, and then radius is equal to sigma 1 minus sigma 2 by 2 is equal to tau max. Center is equal to sigma x plus sigma y by 2 comma 0. Why center is always on x-axis? Because principal stresses should not carry shear stress, so tau is equal to 0. Sigma 1 comma sigma 2 should be on x-axis. R is equal to root of x sigma x minus sigma y by 2 whole square plus tau x y square is equal to sigma 1 minus sigma 2 by 2 is equal to tau max. Point on perimeter represents oblique plane. Point inside circle represent nothing. Football thin pressure vessel. Tensile normal stress outside. Sigma x sigma y. Point in more circle because a spherical r is equal to 0. Sigma 1 is equal to sigma 2. Every plane is principal plane. Point on it. Z pressure, the pressure will be compressive. Here if you consider a point, both are compressive. Sigma x sigma y, it is also a point only. LPG cylinder sigma x sigma y, but these are different. One is PD by 2T, one is PD by 4T. Hoop is PD by 2T, PD by 4T is longitudinal. So sigma x sigma y are there. Sigma x is equal to 2 sigma y. If F is applied like this, we can draw for points A, B, and C. Draw circle for more circle for stresses at points A, B, C. Here A experiences sigma tensile stress, sigma x, and tau xy also. So sigma x tau xy will be like this. So circle we can draw with those 2 points. Sigma c tau xy, tau xy also sigma y. For b we also we can draw if sigma y is negative, so there we can draw tau xy on x-axis. On this axis tau xy you can draw like this. Pure shear, c point c pure shear, so it is a dot in more circle. More circle for 3D. Three axes are given, each has 500, 200, 100 megapascal. Draw for yx, xy, xz, yz separately. Then put three circles here. Then third one will be concentrate xz, xy, yz. R1 50, R2 150, R3 200 maximum shear stress. If material is ductile, fail at 45 degrees from principal plane. Ductile fails in shear mode. Epsilon x is equal to sigma x minus mu sigma y by E. Epsilon y is equal to sigma y minus mu sigma x by E. Pi xy is equal to tau xy by G. More circles same for strain. Sigma x replaced by epsilon x, sigma y replaced by epsilon y, tau xy replaced by pi xy by 2. Universal testing machine, jaw, AO, job, tensile forces, sigma x is equal to F by AO, x long elongation or deflection. F load resistance induced, deflection produced due to load, gradually applied load. It will be like this. Sigma by F is equal to F by AO. Elastic, plastic, half sigma epsilon is equal to sigma square by 2e. epsilon is equal to x by L. Area up to elastic limit, elastic elastic strain energy per unit volume is equal to modulus of resilience. Total area up to failure per unit volume modulus of toughness. Resilience up to elastic toughness total, it is they are strain energies. Anvil should be tough material as it should take impact load. Type of loading gradual sudden impact. Impact factor, if it is dropped from height h, energy conservation F into h plus x is equal to sigma square by 2a into volume al. F into h plus sigma by e into L is equal to sigma square by 2a into al. Solving quadratic equation, F sigma is equal to F by a into 1 plus root of 1 plus 2ae by Fl into h. Impact factor is equal to 1 plus root of 1 plus 2h by delta static. Sigma impact is equal to sigma static into impact factor. Center of mass, center of gravity, both are almost same. Center, when entire mass of body is assumed to be concentrated, where 3D real object is centroid, where entire area is assumed to be concentrated. 2D bodies, geometric center of certain shape, plane 2D bodies. X is equal to integral xi dA by integral dA. X is equal to a1 x1 plus a2 x2 by a1 plus a2. Y is equal to a1 y1 plus a2 y2 by a1 plus a2. dA is equal to y dx is equal to kx square dx. X is equal to integral xi dA is equal to by integral dA is equal to integral kx cube dx by kx square dx. What is moment of inertia? Moment of inertia is inertia of rotating bodies and is analogous to mass of body, which is measure of inertia. Mass, inertia, unique value. Moment of inertia of rotating body calculated with respect to axis of rotation can have many moment of inertia. Area moment of inertia I is equal to ar square. Frame bodies, 2D bodies. Mass moment of inertia I is equal to mr square 3D bodies. What is polar moment of inertia? Axis should be perpendicular plane and passing through centroid J. Radius of gyration I is equal to mk square, k is equal to root I by m. Hypothetical imaginary distance from axis of rotation if entire mass is put as a point mass. Okay. SFD or BMD used to show variation of shear force or bending moment over the length of loaded beam. If m by I is equal to sigma by y is equal to E by R, sigma is equal to my by I. Bending, this is bending moment diagram FL. Bending moment diagram to find where bending stress is maximum. M not equal to 0, M not equal to 0. Fix cantilever beam. Where it is resist, here resists moment, so moment will be there. Fixed both sides resist, so M not equal to 0, M not equal to 0. Simply supported beam, both sides rotation not resisted, so M equal to 0 at both sides. So overhanging beam, M is equal to 0, M is equal to 0. dm by dx is equal to fx. Integral dm is equal to integral fx dx. Integral 1 to 2 fx dx is equal to m2 minus m1. Slope of bending moment diagram at a point gives shear force at that point. dfx by dx is equal to wx. Slope of shear force diagram gives loading diagram. Dmx by dx is equal to 0. uh, is equal to 0. Mx is maximum. If fx is equal to 0, bending moment can be maximum. Can be. So uh, shear force diagram find point where fx is equal to 0. point of cantilever beam on loaded beam where m is equal to 0. Point of cantilever, point of contraflexure, bending moment changes sign. Internal hinge bending moment is equal to 0. Point of contraflexure helps us to know where reinforcement is to be done. What is pure bending? What is pure bending? Give examples. Pure bending means no shear force, only bending moment. One is this cantilever beam with only M applied, no force. Another one is this region, FF. This between these two F, there is no shear force, only bending moment will be there. That is another example. Bending equation and its assumptions. Neutral axis, no bending stress will be induced at neutral axis. Y sigma c sigma t neutral axis. M by I is equal to sigma y is equal to E by R is equal to EI by mx. In case of pure bending, radius of curvature is same everywhere. Assumptions: elastic homogeneous, ECM everywhere, transverse section plane, beam is straight initially. What is section modulus and its significance? Why rail section is I? M is equal to M resisting bending moment is equal to sigma I by Y is equal to sigma Y I by Y max. Sigma max less than or equal to sigma Y. So Z modulus section modulus Z is equal to I by Y max. M is equal to sigma Y Z. Same material, sigma Y is same. So if Z is more, it is strong. Same material, if it is placed like this, I is equal to bd cube by 12, y max is equal to d by 2, z is equal to bd square by 6. If this is db square by 6, so bd square by 6 is bd, this will be more. For rail I section modulus is maximum. Here and here, as material is more, distance from neutral axis. Beam it will undergo like this. Column, it will undergo buckling where length is more. I is equal to pi d power 4 by 64. Z is equal to I by y max is equal to pi by 32 d cube for circle. Thin pressure vessel and cylinder, LPG cylinder, T less than or equal to D by 15 to D by 20, D by 20. Spherical, sigma 1 is equal to sigma 2 is equal to PD by 40. Cylindrical, hoop circumferential or hoop stress length L, sigma P into DL, that is projected area pressure. P into DL is equal to 2 sigma in 2 sigma into L into T is equal sigma 1 is equal to PD by 2T. Longitudinal stress sigma 2 is equal to PD by 4T. Tau max is equal to sigma 1 minus sigma 2 by 2 is equal to PD by 2T minus PD by 4T by 2 is equal to PD by 8T. More circle, sigma 1 sigma 2. LPG cylinder, this is welding circumferentially. Welding because longitudinal stress is less than circumferential stress. Efficiency of longitudinal or circumferential joint. Sigma 1 is equal to PD by 2T into eta L. Eta L is like this, longitudinal or hollow cavity. Sigma 2 is equal to PD by 40 into eta C. Epsilon 1 is equal to circumferential is equal to sigma 1 minus mu sigma 2 by E is equal to delta D by D. Epsilon 2 is equal to longitudinal is equal to sigma 2 minus mu sigma 1 by E is equal to delta L by L. Column and structure. A column and strut. Column, beam, axial, vertical column, direct compressive or crushing stress, crushing strength. Strut, connecting rod, axial compressive force, slender, length is far more than cross section. That is strut. Bending stress induced buckling. Column, short compressive sigma c is equal to F by A. Long buckling Euler's analysis M by I is equal to sigma by Y. Medium both direct compressive and bending stress Rankine analysis. Euler equation crippling load PE. Only column is long, only buckling and or bending stresses P is equal to pi square EI by LE square. EI flexural rigidity. Both cases both sides hinged. LE is L, P is equal to pi square EA by EA K square by L square. Okay. Fixed one and free, then 2 L is 2L. Fix both ends fixed. L is L by 2. Fixed hinged L by root 2. P pi square E A K square by L E square. Crippling stress P E by A is equal to pi square E by L E by K whole square. Slenderness ratio S is equal to L E by K. If S is more, we can use Euler. Slenderness ratio is more, we can use Euler. Rankine formula P is equal to safe load is equal to sigma C into A by 1 plus A LE by K whole square. A is equal to sigma C by pi square E. A is Rankine constant. Shear stresses F tau is equal to F by A. Transfer shear stress, average stresses on top, inside, complementary stresses or and bottom, outside. Complementary horizontal shear stresses at y, tau y is equal to Fa y bar by Ib. F shear force A shaded area, y bar distance of G of shaded area from neutral axis. Distance of G from neutral axis. For rectangle, tau average is equal to F by A. Tau max is equal to 1.5 tau average. Tau max is equal to 4 by 3 tau average. For circle, tau max 4 by 3 tau average. For rectangle, tau 3 by 2 tau average. This is shear stress distribution diagram. Where there is hollow cavity, the shear stress is going more. Here the hollow more, tau max more. At tends 0. So torsional shear stress tau, when torque T is applied, T by J is equal to tau by R is equal to G theta by L. Tau is equal to TR by J is equal to 16 T by pi d cube. J polar moment of inertia. J is equal to pi by 32 d power 4. J is equal to pi by 32 into do power 4 minus di power 4. T is equal to tau into Zp. Zp is equal to J by R. Zp polar modulus. Shaft power P is equal to 2 pi nt by 60. T is equal to torque transmitted average value. Axial rigidity EA delta X is equal to PL by AE. High AE, more load required to produce small displacement. Flexural rigidity EI, M is equal to EI by R. Torsional rigidity GJ, T is equal to JJ by L into theta. Stiffness is equal to T by theta. Stiffness F is equal to Kx, K is equal to F by X, with P by delta X is equal to EA by L is equal to stiffness. Stiffness is rigidity per unit length. E Young's modulus, EA rigidity, EA by L stiffness. Stress strain diagram. F AO LO gauge length universal testing machine. Sigma is equal to F by AO is equal to engineering stress. So epsilon is equal to delta L by LO engineering strain. Sigma epsilon sigma y P elastic plastic mild steel low carbon for low carbon steel elastic plastic upper proportional element elastic upper yield point lower yield point intermolecular reasons it will decrease the strain hardening universal testing machine necking 25% up to 25%, 0.12%, 20%. Resilience or toughness area, ductility, brittleness, malleability, length, epsilon, till what epsilon it is going. Elasticity, rigidity, stiffness, slope, strength, height of stress. Brittle cast iron, glass, ceramic, concrete. Sigma epsilon less than 5%, it will be failed. Uh, Ductile copper, aluminium. Ductile, it will be like this. For ductile offset method, sigma y is equal to question mark. The offset method epsilon 0.2% or 0.02%. 0.2% or 0.002 is considered as epsilon. Tangent at O, parallel offset at 0.2 epsilon to find yield strength, proof strength. Sigma T, epsilon T, sigma engineering strain, engineering diagram is like this. True is will be keep on increasing. Sigma T true stress is equal to F by A instantaneous. Epsilon T is equal to dx by L instantaneous. Epsilon sigma T is equal to 1 plus epsilon E into sigma E. Epsilon T is equal to ln of 1 plus epsilon E. Epsilon E is equal to delta x by LO. Sigma is equal to F by AO. Sigma epsilon plastic it will be like this, mild steel normal, rubber will be like this, rubber is different. Ceramic, glass, concrete is more slope is more, but it will be like this. Aluminium, ductile, mild steel, top. Deflection of beams. Y deflection, theta is equal to dy by dx is equal to slope of deflected beam. R radius of curvature, R is equal to ei by m. Maculus method, mx is equal to minus ei d square y by dx square. D square y by dx square is equal to minus mx by ei. Fx is equal to dmx by dx. Dfx by dx is equal to wx is equal to minus ei d square y by dx square. At fixed ends, theta is equal to 0, y is equal to 0. Fixed beam MA, MB, W, RA, RB. If they ask how to find the bending moment, then separate loads and moments separately, draw diagram, superimpose both of them. With the load it will be like this, with only bending moments it will be like this. Superimpose both of them, negative, positive, negative. These are 2 points of contraflexure. If a fixed beam it is like this, here also same process, first only load, then only moment, from that we can get point of contraflexure, we can get conjugate beam, imaginary beam whose load diagram is m by ei diagram. For actual beam, slope of actual beam is equal to load at same point on conjugate beam. Deflection of actual beam is equal to mx of conjugate beam. Slope is load, deflection is mx of conjugate beam.